everyone, good afternoon to all of you. So today we are going to learn about an important topic for both JEE as well as NEET, and that is capacitors and dielectrics. Combination of these two will give you at least a minimum of one or two questions in every session of JEE as well as in your NEET examination. So today we will learn in one shot all about this capacitors and dielectrics along with few examples and also most frequently asked PYQs here itself solved in the video. So let's start our session without any delay. So starting with introduction to the dielectrics, I would like to go ahead. What is a dielectric? If anyone could know, try to answer yourself. Just memorize the answer. What do you mean by a dielectric? So a dielectric is nothing but simply I can say a substances, okay, substances which do not possess free electrons. What do you call which do not possess free electrons, or very less, they possess very less number of free electrons. So either they don't have free electrons or they may have very less number of free electrons. And why these free electrons will be used to constitute electric current? For what purpose are we need to have these free electrons? To constitute electric current. And such substances which do not possess those free electrons are called as dielectrics, and these materials are called as dielectric materials. So mostly the dielectric materials are made up of, okay, I mean like the classification was there for this. There are different type of them. Whatever they among them, they are your non-polar molecules. These are few molecules which can be used, but these will have no net dipole moment. These materials will not have no net dipole moment. So therefore examples for such polar molecules are H2 as well as N2. And there are even for us some polar molecules which can be used as dielectric, and these polar molecules will have almost permanent dipole moment. So fixed, that is a fixed dipole moment, and that will be lasting forever. So that is called as your permanent dipole moment. Examples like you can see HCl, we do have H2O, etc. So these are your dielectric materials which probably we can use here in our whatever the topic we are going to learn here, and we are trying to understand both dielectric and capacitor utilization in our day-to-day circuits and all examples. So as we started with dielectrics, let us see about the next term called as dielectric polarization. So what is this dielectric polarization? So simply discussing just above only we have classified the dielectric materials based on the dipole moment, right? So simply saying about this dielectric polarization is also termed as, so dielectric polarization is defined as net dipole moment or the total dipole moment of a dielectric material ratioed for its volume. So the net dipole moment per unit volume of a dielectric material is called as its dielectric polarization. So therefore this polarization is always directly proportional to the electric field applied across the dielectric material. And this removing the proportionality constant, I get a constant called chi, and this one already we know this is called as electric susceptibility. What do you call this one as? Electric susceptibility. So in this way we can define this dielectric polarization. And mostly just there is a kind of a note point I would like to introduce here, a small point I would like to add. A uniformly polarized, see here I am writing clearly where theoretical questions can be helped out. So a uniformly polarized dielectric. What do you call this one as? A uniformly polarized dielectric. amounts to. What do you mean by amounts to? Which gives the clarification or information about. Abouts to. See here, induced surface charge density. What information will it give you? Induced surface charge density. What information? Induced surface charge density. Mostly we will think that it will be giving you the entire volume charge density. So that's why for a clarification, it will give you only about induced surface charge density, but not about volume charge density. So this is quite important, and you need to remember this point very carefully coming to in a theoretical question. So any uniformly polarized dielectric which will amount or will give you a clarity about only induced surface charge density only, but not about a volume charge density. So the reason already we know that one, net dipole moment will be classified between the two faces straight away. So for such cases, if I consider a cube material or a cube, if I consider in this way, see here, let me show a cube drawn neatly. So see here in this way. So say this is a cube charged on either side on the both the surfaces. So for this one, I would like to calculate the polarization. What do you call a dielectric polarization? Say now the cube length is of L and one face of it is completely negatively charged, and say this is minus Q, and the other face is completely charged to positive, and say this is plus Q. So therefore already we know this acts as like a dipole only now. So therefore net dipole moment will be, already we know that dipole moment formula is equal to product of the dipole length into the any one of the charge present in the dipole. So here what I can write this one as L into Q. So that is your charge. So therefore what is the volume of the cube over here now? L cube. That is side into side into side. So now from this what I can get a clarity about it? Polarization. What is polarization? Already calculated just now. Net dipole moment per unit volume of a dielectric. What is net dipole moment? L into Q by what is the volume? L cube, which seems to be, what is this? Charge per unit area. What is this charge per unit area called as? Surface charge density, that is sigma. So that's what the above statement is. So this is called as induced surface charge density. Induced surface charge density. So this is what the understanding what I would like to give you clarity, that a uniformly polarized dielectric amounts to induced surface charge density only, but not a volume charge density. So please make a note as a clarity for this one, clarification. And also you can even write this sigma, that is induced surface charge density, as dot product of polarization and a unit vector. What is this unit vector? N cap. It is a unit vector along which direction it will be? Outward to the surface shown, and also it will be normal, always normal to the surface on which the charge was considered. So this is all about your introduction to the topic of dielectrics and what is your induced surface charge density. So now let us understand the induced charge or bound charge, where it is going to be between the two parallel plates. So any two charged plates are there or charged surface are there, between those two induced or bound charge. Now let us understand about this concept called induced or bound charge, and say that is denoted by Q dash for time being. So let me consider two charged sheets were there for me, and those charged sheets were parallelly placed on either side for me in this way. So you can say this is one charged sheet placed onto the left, and say the same one more charged sheet I have considered over here, and see now in this way. Now say this left charged sheet is completely positively charged, so therefore its surface charge density will be positive, and say its charge be Q, and initially the medium separation between these two be air. So now the other charged plate, other is charged to a negative, so this is minus Q. So what do I understand over here? Already we learned in our previous chapters in electric field concept. What was that? This the electric field produced by each surface. Here positively charged surface will have an electric field towards right side, and that electric field is given by E1 is equal to sigma whatever your surface charge density by 2 epsilon naught, as it is a non-conducting sheet. And for the negative plate it also will be in the same direction towards right side only, say that is E2 again, and that is also given by sigma by 2 epsilon naught. So what is the net electric field passing between positive plate to the negative plate, and that net electric field here I would like to consider this one as E naught. And this now E naught is given by the net electric field due to the two charged plates, that is E1 plus E2, which will account to E naught is equal to simply sigma naught by epsilon naught. So sigma naught I can consider as initial induced surface charge density. So this can also be written as, in short words, Q by A epsilon naught, since sigma naught is equal to Q by A, or surface charge density. So in this way I can do. So now what if I place a dielectric in this, between these two? What if I place a dielectric between these two charged plates? So that is our lesson right now. Here we are learning about. So now I would like to place the same positive, everything pura, this is positively charged plate previously considered, and this is a negatively charged plate as discussed. So now say this is having a charge of plus Q, and now this is minus Q. Now I introduced another or a medium other than air called as now my dielectric. What do I call this one as? Dielectric. And this dielectric is having a constant called K, dielectric constant K. Now see here, as the leftward plate is positive, all the negatives or negatively charged carriers or the dipoles will induce on the left side of the dielectric, and as the right side plate is negative, all the positive ions get induced onto the right side of the dielectric. So now in this case, if you observe carefully, the initial electric field will be in which direction? From positive to negative, that is E naught. And due to this induced charges in the dielectric, there will be an induced electric field which will be from positive to the negative in the left side against the direction of E naught. So now this is my point over here. The net electric field induced because of these two, I mean like because of the presence of the dielectric between the charged plates, is E. And this E is resultant of these two electric fields. What are those two? Initial electric field E naught and induced electric field EI. Done. And what is this E called as? E, we got a net electric field because of the presence of your dielectric. So therefore, in starting only, when we learned about the force and using a Coulomb's law and electric field K Q by R square, where K is 1 by 4 pi epsilon naught, in a medium 1 by 4 pi epsilon. So epsilon R into epsilon naught, where epsilon R is called as dielectric constant. So using that formulas, what I could write this E as 1 by K into original electric field E naught. So this is very important, guys, and this is quite interesting to add this point over here. So just adding that over point over here, I would like to add this one. See, E is equal to, now directly I can add E naught by K is equal to E naught minus EI. So what is the heading? Induced or bound charge. So I'd like to learn about induced electric field now. So therefore induced electric field from this EI is equal to straight away E naught into 1 minus 1 by K. So thus here ends the topic for us. Induced electric field is observed as E naught into 1 minus 1 by K, where E naught is the initial electric field and K is the dielectric constant. So from which, where electric field is given by, previously we have learned, see here, the electric field is given by Q by A epsilon naught. So if E naught is Q by A epsilon naught, E induced will be Q induced by A epsilon naught. So let the induced charge be. From this, let induced charge be Q dash. So therefore EI can be written as Q dash by same area, same medium over here, and this is E naught is also equal to the same thing. What is this? Q by A into epsilon naught, and this is 1 minus 1 by K. So from which I get the induced charge Q dash is equal to Q into 1 minus 1 by K. So the charge gets decreased by an amount or increased by an amount, 1 by K. So you need to identify this K value. If using the K value, whatever the charge stored or charge induced on the charged plates using the presence of the dielectric, we can calculate. So this is all about your induced charge. And coming to the next thing is electric displacement. So this electric displacement, we can use this concept in EM waves, displacement current बोलते हैं उसको. So there we can have this idea about electric displacement, and this concept can be utilized there. So from this electric displacement, I would like to write sigma naught, that is equal to d bar is the displacement vector into n cap. So previously I have written the same thing, and now we are writing here. So therefore sigma naught is equal to, what could I get it? Epsilon naught into E bar, that is your electric field, plus polarization, dielectric polarization dot n cap. So the displacement, electric displacement, can be found using this equation straight away. These are short forms where we can learn, or simple smaller concepts I would like to explain you in this there. And next, some important formulae or important conclusions I can give you. That is, when a dielectric is placed in electric field, what are all the conclusions we can draw out is being taught now here. So dielectric placed in electric field. So what all I can get now here? Straight away, the induced electric field, whatever it is, can be written as E naught into 1 minus 1 by K, through which induced surface charge density can be written as sigma naught into 1 minus 1 by K. Similarly, induced charge can be written as Q into 1 minus 1 by K. So wherever necessary, you can use the formula conversion between induced as well as initial electric fields, or surface charge density, or charges. So this formula we can use straight away. And now let us enter into the topic, our capacitors. So starting with this, we will start about capacity of an isolated conductor. So starting with capacity of an isolated conductor. So what do you mean by this capacity called as? Ability to store. Ability to store. So straight away you can write, so at any instant, capacity of an isolated conductor, at any instant I can write this one as, at any instant, charge on a conductor. Remember, listen here, charge on a conductor is directly proportional to potential applied at that instant, or potential difference, straight away. So charge on a conductor is directly proportional to potential or potential difference applied at that instant. So removing the proportionality, what do I get? Q is equal to C into V. That's it. We got the equation, where C is called as a proportionality constant and named it as capacitance. Named it as capacitance. And the capacitance mainly depends on, the capacity mainly depends on, so what are all the things it will depend on? Shape, and at the same time it depends on size, and also it depends on permittivity of surrounding medium, and on which it doesn't depend on. So it doesn't depend on what are all those Q or V. So charge or potential of a conductor, the capacitance doesn't depend, and it only depends on shape, size and epsilon. What do you mean by epsilon? Called as permittivity of the surrounding medium. And the SI units or the units I can just write down here. The units of capacitance, so is basically given by C is equal to, I can write Q by V, that can be written as Coulomb per volt, and this Coulomb per volt is named after Farad and denoted by capital F. And practically we will have microfarads. Practically the capacitance storage will be of microfarads. Clear? So as we started and we entered into the topic, and now let us see for various objects capacity can be calculated. So among that is first one, capacity of an isolated sphere. Capacity of an isolated sphere. So if I just consider, if I draw a diagram, a sphere, a round one, which will be a dimensionally, I mean like polygon I can say, and having a radius r, and now it is having positively surface charged density it is been having, and say at a point there are multiple points I am having A, B, C and all etc. So at all those points I would like to consider the potential V as 1 by 4 pi epsilon naught Q by R simply. And what is the formula for capacitance? C is equal to Q by V. So from that I can write this one as simply C is equal to 4 pi epsilon naught times R. So capacity of a isolated sphere is 4 pi epsilon naught times, it only depends on the radius. At the same time epsilon naught, that's what we learn here, size and shape, so and permittivity. So this is the thing we can use. And if I consider such kind of a sphere, what do I do have? And let us write these all the things also the same, independent of, I mean like it depends on dimensions, nature of medium etc etc, already we proved it, and it is independent of charge, thus C equal to 4 pi epsilon naught, there is no traces of charge and no traces of potential etc. And now very well known sphere for us is Earth. So if I would like to calculate the capacity of Earth, if I would like to calculate, then C E is equal to, straight away what I can write this one, 4 pi epsilon naught into radius of Earth is 6.4 into 10 to the power of 6, and 4 pi epsilon naught value is 1 by 9 into 10 to the power of 9 into 6.4 into 10 to the power of 6. So which will give me the capacity of Earth is nearly 711 microfarad. 711 microfarad. So likewise, if we know the potential and we can calculate the capacitance of any object. And what exactly this principle behind the capacitor? Let's learn about this one. So principle of capacitor. Principle of capacitor. So in a capacitor, straight away the I mean like I would like to write everything because it's an important. So the whole statement I would like to mention over here. So in a capacitor, maximum charge holding capacity. Maximum charge holding capacity of conducting plate. Holding capacity of conducting plate, whatever we are considering previously, conducting plate is increased by placing neutral earthed plate near to it. Near to it means whom? Conducting plate, near to it. So what is the reason for this one? It will, which lowers its surface potential, which lowers its surface potential thus increases charge holding capacity. So using this, two charged plates we can place side by side and make sure one is earthed to make sure this charged plates hold the maximum charge, and that is the principle of capacitor. So now let us enter into the topic. As started already principle of capacitor, now I would like to learn about the parallel plate capacitor, most important one, and this is the crucial heart of the chapter. That's it. So parallel plate capacitor. So I would like to show you a diagram, a three-dimensional view of this parallel plate capacitor. Just imagine, say this is one kind of this is a one parallel plate. What do I have? And this is another parallel plate. So plate in the sense it's a two-dimensional asset, right? So let me show that two-dimensional thing also to you, how it's gonna be. So see here, imagine it is being present behind in this way. So now this is one charged plate, and this is one more charged plate. Based on the definition, I would like to say that one of the charged plate is neutrally earthed or earth. I mean, like this is, I was connecting it to the earth. So therefore this whole charged, this plate will be of negatively charged thing, and this plate will be of positively charged plate. So therefore the distance between the two charged plates be d, and say the electric field is flowing from positive to negative here, and say the medium present between these two plates is air, and say the charge present on each plate be q, and the cross sectional area of the plate be a. So therefore surface charge density is given by q upon a. So if I would like to derive this formula for the capacitance of this parallel plate capacitor, it's gonna be easy. So from our definition, what is E electric field? So that is simply Q by epsilon naught times A. Already well known this one, previously only we calculated this one. But already what do we know? But we know E is equals to, from other definitions, E is equal to V upon D, potential difference between the two plates, and the distance separated by the two plates is d. So using these two combinations, I can straight away write the capacitance formula. C stored, I mean capacity storage of this parallel plate capacitor is epsilon naught A by D. Most important yet powerful formula for finding the capacitance of a parallel plate capacitor. So I would like to give you many stars for this. You can just remember this formula. Clear? C equal to epsilon naught A by D. So now I would like to show you one numerical which was asked in PYQs on this model only, which seems to be a bit tricky, but once if you can understand, it's gonna be a most easiest topic. So let us see that one of a PYQ question, whatever previously asked. So now I can show you this one. See here. So I would like to select this one, and this PYQ I would like to explain you now. So right, see here, a capacitor is made of a, what they say, flat plate of area A, and a second plate having a stair like structure as shown in figure. If the area of each stair is A by 3 and the height is D, the capacitance of the arrangement is. Okay, now I would like to draw the same diagram over here so that it will illustrate you in a clear cut way understanding. Say this is the bottom plate. Let me suppose this is connected to the earth, okay, for our understanding. And now what did they say? The other one is like a staircase. The other side was arranged as a staircase in this like. Done? Beautiful. And now the each cross-sectional area of this each staircase they have given is A by 3, I mean like identical A by 3, and this is also A by 3. And the distance given between each step is, this is D. And the height of the another step is also D, and this is also D. So what I can write now, for our understanding, the distance between these two plates is D, and the distance between these two plates is 2D, clear. and the distance between these two plates is 3D. More beautiful. Done. So I had 3 parallel plate capacitors connected together straight away. So therefore I can add up the entire capacitance directly. So adding up the entire capacitance, I would like to get individual capacitances. So therefore C1 is equal to epsilon naught A. A means how much? A by 3 by D. Distance is D. So therefore this can be written as epsilon naught A by 3D. And next C2, that is equal to second one, middle one. So epsilon naught A by 3 by 2D. So this can also be written as epsilon naught A by 6D. And next C3 can be written as same epsilon naught A by 3 by 3D. And now this can be written as epsilon naught A by 9D. See children, this is one of a PYQ where reflected from our matter itself straight away. The most important one, right? So therefore net capacitance now. C is equal to, let me add up all these. So among which I can take common epsilon naught A by D. So it is gonna be 1 by 3 plus 1 by 6 plus 1 by 9. So LCM for 3, 6, 9 is LCM for 3, 6, 9 is 18. So therefore epsilon naught A by D into 18. So therefore 3 6 are 6 3 are and 9 2 are. So which will give me the capacitance of 11 epsilon naught A by 18 D farad. See how beautiful the question was. Seems to be a bit tricky, but yet easy. Okay, the questions are gonna be in your competitive exams like this only, children. They seems to be tricky, that's it. But when you apply the concept more particularly like this, whatever we did now based on the formula, it's gonna be beautiful. And it's never ending process, the learning. Understood? So try doing in this way only. And this is done. And now, what if I introduce a dielectric between these two parallel plates? So now this is the medium present here, air, right? So now I would like to show you parallel plate capacitor with a dielectric. So let us see this one now. Parallel plate capacitor, parallel plate capacitor with dielectric. So the same concept, now I am placing a dielectric between these two. So for in short, I would like to draw the diagram simply so that you can easily understand instead of drawing a big diagram like previously. So now say this is your two parallel plates and each one is charged positive, this one, and the another one is negatively charged. So now what do I place in the middle? I have placed a dielectric. What did I place? I have placed a dielectric in the middle and say its dielectric constant be K, and now the electric field, net electric field is gonna be towards right side. So using entire derivation and all etc., instead wasting your time, I'd like to just make you a clarity that the capacitance of this dielectric, I mean like a capacitor when dielectric was introduced between the parallel plates, is given as C is equal to, see, remember simply epsilon naught A, previously it is D, right? Now here D by K, that's it. Epsilon naught A by D by K, where K is the dielectric constant. Where K is the dielectric constant. So now I can write this one as C is equal to K times epsilon naught A by D. And what is this epsilon naught A by D? Capacitance of these two parallel plates when the medium is air. So therefore I can write C dielectric is equal to K times C when there is no dielectric, that is air. Simple, sir. You can remember these concepts in a easiest way, which will be bit easier for you. Okay, so this is the logic we can use. And now What if there are multiple dielectrics? What if there are multiple dielectrics placed for us? So let us try to understand that also. There are some multiple dielectrics placed between these parallel plates. So now let me draw. This is one parallel plate, and this is one more parallel plate. Okay, so now they have placed multiple dielectrics between these two. Now they have placed multiple dielectrics between these two straight away for me. So now what I would like to draw, multiple dielectrics between these two shown in this way. See here, this is one dielectric, and this is one more dielectric placed, and this is the another dielectric placed close by. There are no gaps. Okay, na? The close by they are placed. So now for this one I would like to find out the effective, like the capacitance stored between these two. Say each dielectric is having a dielectric constant K1, K2, K3, and say their thicknesses are T1, T2, T3. And now remember that the width of the parallel plates is now equal to T1 plus T2 plus T3. So total, understood, the total width between the two parallel plates is equal to the sum of the thickness of the dielectric constants. So therefore capacitance for this one is basically epsilon naught A by, what do I say, D by K for each dielectric. But now how many dielectrics are there? 3 dielectrics are there. So therefore it is gonna be epsilon naught A by, exactly what you said is correct. So it is gonna be initially, what is this one? The thickness of the first dielectric is T1 by its dielectric constant K1. Thickness is T2 by its dielectric constant K2. And the thickness is T3 and its dielectric constant is K3. Done, gone guess. So in this way we can find out the capacitance. What if there are n number of dielectrics? What if there are n number of dielectrics placed in this, in the way shown in the figure? So for that what I can write straight away, C equal to epsilon naught A upon, how many are there? Infinite are there. So let me write T1 by K1 plus T2 by K2 plus so on. You can use this concept straight away. Okay then. And now what if the dielectrics are again introduced with a combination of air medium also? Okay na? So combination of air and dielectric. Combination of air and dielectric. What if it was given in this way? So now let me explain only with one thing only, and then we will go to the next. Okay na? So first of all understand this is a parallel plate, one of the parallel plate, and now this is another parallel plate. Now I do have one dielectric. Okay, I do have one dielectric over here introduced in this way, and say its thickness be T. For time being, let's say its thickness be T and its dielectric constant be K. And now where was the air present? Now this is the air, and what is the width of these two plates be? D. So what will be the thickness of the air present? D minus T. Done. So therefore from this logic what I would like to write, so for air will be C equal to how much? Epsilon naught A by D. This is in air. And what if the dielectric was present? Ck is equal to epsilon naught A by whatever you say, D by K. But now it is not in that case. Now it is a combination of air and dielectric, right? So therefore the new capacitance is now going to be C is equal to, see, remember carefully, epsilon naught A by, the logic you see here, epsilon naught A by, write the distance for which the air was present. What was the width for the air was present? D minus T. Okay, and then write the dielectric thing. What is the width for the dielectric present? T. So therefore it is going to be T by K. That's it. Very simple and short. So therefore now on rearranging the terms, what do I get this one as? Epsilon naught A by D minus T into 1 minus 1 by K. So this formula I can use for the combination of air and one dielectric. Air and one dielectric. You can ask me, sir, now what if there are multiple dielectrics? What if multiple dielectrics plus air combination? Let us see that also. So multiple dielectrics plus air combo. Previously just now learned single dielectric and air. Now here it's a combo of multiple dielectrics and then air. So now let me show you this one. So now this is a parallel plate capacitor which was now filled, assuming that it was now filled with different things. Right, see the first dielectric. Say the next dielectric. And one more. And also one more. Different dielectrics are present in addition with what you call as air also. So say this is now air and the width of these dielectric, I mean like parallel plates is D, and say each one is T1 and its dielectric constant be K1. This is T2, its dielectric constant is K2, and this is T3, its dielectric constant is K3, and it is T4 and dielectric constant is K4. Now from the picture you can say me clearly that the width for which the air was present, the width for which the air was present, exactly, absolute, what you said is correct. D minus of T1 plus T2 plus T3 plus T4. Beautiful. So now this is air capacitance straight away. So therefore the resultant capacitance C is equal to what you can expect now, epsilon naught A by straight away I would like to write this one as, so listen here. First of all, for the air, for what distance or width the air was present, D minus of T1 plus T2 plus, let me say there are n number of dielectrics, so plus so on, done, air was done, and plus now n number of dielectrics, T1 plus T1 by K1 plus T2 by K2 plus so on. So now in this way I can find out the entire capacitance of the total dielectrics plus air combination. Clear guys? So now see, such a beautiful thing, only for the air we need to find out that distance, and then the remaining as usual for the dielectric whatever you are writing straight away. And for this also I would like to show you one numerical which was asked in a PYQs earlier. So let me show that also to you now. Right. So you can see this is the question they asked for us. So as shown in the figure, two parallel plate capacitors having equal plate area of 200 centimeter square are joined in such a way that A parallel to B. Done. Sorry, A not equal to B. The equivalent capacitance of the combination is now X epsilon naught farad. X times epsilon naught farad itself. Now for that, what are they asking you to find? The value of X is. For that they are asking you to find the value of X is. Okay. So now let us try to solve this one in an easier way for us. How can we solve this one? Any ideas? Just give a try. Yes, just give a try. Right, let us start. Solution. First of all, try to understand this entire two parallel plates are there now for timing, right? So everything. What was the distance they have given? C is equal to 1 millimeter. Now what about A? What about B? I don't know. And they said that A is not equal to B. See here. We know, as he knows that as this is 1 millimeter, from the observation we will think that these two are equal. So that's the condition they have given for us, A not equal to B. Okay, and what was the total width? They have given 5 millimeters. So now with this what I can do, you can observe, see here, if I just say this is one parallel plate capacitor and this is one more parallel plate capacitor, so this is two are connected in, how they are connected in series. How are they connected? These two are connected in series. So now uh, the combination is a series combination. Clear? The combination of capacitors is series one. So when two or more capacitances connected in series, what is the equivalent capacitance? I know 1 by C series is equal to 1 by C1 plus 1 by C2. Now let me write C1 value. C1. So C1 is equal to, from our basic formula, epsilon naught A by D. What is the distance? A. And similarly, what is C2 formula? Epsilon naught A by D. What is the D? B. Done. So now let me substitute there. So 1 by C series is equal to 1 by C1. That will be A by epsilon naught A, and 1 by C2, that is B by epsilon naught A, which will give me A plus B by epsilon naught A. See, it's clear that total width is 5 millimeter. This is 1 millimeter. And what will be A and B together? So A plus 1 plus B equal to how much? 5. So if 1 goes to the other side, what will be the value of A plus B equal to? 4 millimeter. Done, I got the answer. So therefore this is gonna be so easy that 4 millimeter by epsilon naught A, and this is 1 by C series, but what do I require? C series is equal to epsilon naught A into area, how much? 200 centimeter square, means 1 centimeter is 10 power minus 4 meter square, and by what was this one? 4 millimeter, means 4 into 10 power minus 3. So therefore I can straight away give you the answer now as 4 ones are 450s are. So this is going to be straight away 10 power minus 3 was up 10 power plus 1. So this is 5 times epsilon naught. And what did they give you for us? This is equals to, it seems, x epsilon naught. So therefore x is equal to 5. See, this is also a PYQ. Previously asked question in our competitive examinations like JEE many times and once in NEET. So see, such an important concept which was easily explained and also learnt very easily. So this is the way you need to learn, guys. Make sure that the concept was injected into your minds perfectly. And now let us see a combo question. As you can ask me, sir, you did not explain us the combo question, right? So I would like to give you a combo also now for you. Example, basic example I would like to write here on the screen itself. Say like two parallel plates are there which are separated by a width d, and now say there is a metal dielectric which is having a thickness of d by 2, then what is the effective capacitance? Okay, so already we know the formula, that is C is equal to epsilon naught A by d minus t plus t by k. Okay, but what was the dielectric used here? The dielectric used here is metal, and already we know that for a metal dielectric constant will be how much? K is equals to infinite. Remember, K equal to infinite. So therefore C is equal to epsilon naught A by simply d minus t, that is d minus d by 2. So which is going to be 2 times epsilon naught A by d. Got it, guys? So in this way we can use this, like learn the combo questions easier way. And now let us enter into our most easiest and interesting concept, that is combination of capacitors. What was that? Combination of capacitors. Most of you will be waiting very anxiously to learn this one only. So combination of capacitors. So at the last, I would like to explain a few concepts also. Presence of dielectric, what are all it can affect us. Okay, one after the one we will be learning. Okay, so first one, when these capacitors are connected in series. Capacitors connected in series. What happens when the capacitors are connected in series? So let me show, there are three capacitors for me. How many are there? Three capacitors which are connected in series. Done. There are three capacitors connected in series to me, and this is also connected to some kind of a voltage source. Clear, guys? So now say this is positive and this is negative. Due to this positive present over here, on this plate positive charge will be induced. So on the other charge, negative. Because of this negative, here it will be positive, and this is going to be negative. Because of this, the other side positive, and here negative. So what I can clearly understand, that the capacity of this one is C1, C2 and C3. As the charge was induced because of the one each other plate, the charge present on the each capacitor or induced on the capacitor Q1, Q2, Q3 remains the same. That's it. So Q1 is equal to Q2 is equal to Q3 is equal to total charge Q. And who is gonna distributed? The potential across the charges, capacitors, is gonna distributed or shared. So is equal to V. So that's it. From this, what I can calculate simply, V is equal to Q upon C. So using this logic, I can calculate when these are connected in series. So 1 by C series is equals to 1 by C1 plus 1 by C2 plus 1 by C3. If there are n number of capacitors connected in series, it is gonna be 1 by C1 plus 1 by C2 plus 1 by C3 plus so on. That's it. Clear, guys? So this is when capacitors connected in series. And remember, as this is a parallel combination, and there are, I would like to give you some note points which will be better easy for you to understand. That is, the C series will be less than always least of C1, C2, so on. N number of capacitors connected in series, out of which the least capacitance will be there, lesser than that, the equivalent capacitance C series is gonna be. Clear? And one more thing I would like to give you or understanding in this is the ratio of the charges. So Q1 is to Q2 is to Q3. Since all are identical charges, we will have same 1 is to 1 is to 1. And voltage ratios, V1 is to V2 is to V3 is equal to simply 1 by C1 is to 1 by C2 is to 1 by C3. And most important now, and most important in this, since voltage is getting distributed, important point I would like to give you, add on. So voltage on each capacitance, voltage drop on each capacitance, what was that now? V1, V2, V3. I would like to calculate that one. So V1 is equal to, remember children, V1 is equal to simply 1 by C1, okay, by 1 by C1 plus 1 by C2 plus 1 by C3 into V. That's it. For V2 it is gonna be, just give a try. Very good. 1 by C2 by 1 by C1 plus 1 by C2 plus 1 by C3. That's it. In this way you can simply straight away solve kar sakte. In short, I can write 1 by C1 plus 1 by C2 plus 1 by C3 means 1 by C series only. 1 by C1 by 1 by C series means C series by C1. So I can even write V1 is equal to C series by C1 into V. So similarly others. Similarly V1, V2 and V3 you can calculate in this way. So this is a combination of capacitors when connected in series. If you would like to do an example, just take two capacitors in series and just give a try for capacitance as well as potential across those two capacitors easier way. And now let me go through the another one, capacitors connected in parallel. So parallel combination you can understand, I guess. So the parallel combination of capacitors is this one. So now having three capacitors connected in parallel as shown. Since each capacitor is having a different path connected to the source as shown in this way, the charge passing through each one will get shared. So now this is Q, due to which it gets shared as Q1 sorry, Q2, and this is Q3. So charge induced on the plates of this capacitor will be Q1 plus Q1 minus Q1, and this is Q2 plus, and this is Q2 negative, and this is plus Q3, and this is minus Q3, and this is a potential V. So therefore throughout across everyone, see this is capacitance C1, C2, C3, the potential remains same. So therefore in parallel, when connected in parallel, what are the conclusions I can write directly? V1 is equal to V2 is equals to V3 equals V, and at the same time Q, total charge equals Q1 plus Q2 plus Q3. From this I can get the net effective capacitance as CP, parallel combination, is equal to C1 plus C2 plus C3. Simply done. This is the effective combination when the capacitors connected in parallel. And if there are n number of capacitors, C1 plus C2 plus C3 plus so on. And here also there are some important note points we can just list out whenever you need. And there your voltage ratio will be same 1. Voltage ratio is going to be 1:1:1, and charge ratio is going to be C1:C2:C3. Charge ratio is going to be C1:C2:C3. And individuals, I require right individual charge. So charges present on individual capacitance. For that the formula written as Q1 is equals to, just make a note, Q1 is equal to C1 by Cp into Q. Simply Q2 is equal to C2 by Cp into Q. Q is total charge. Similarly Q3 is equal to C3 by Cp into Q. Done. So you can use this formula and you can just easily find out the effective capacitance also. Clear? Right. So this is all about your combinations of capacitances, parallel and series, etc. And at the same time, now I'd like to show you a few things like a special combinations or all, etc. Those are also done for us. And now what was the thing I would like to give you is effect of dielectric. Okay, now effect of dielectric, what are all the things it is gonna change. So before doing that, I mean like before learning that, I would like to explain you one more thing also, that is energy. Okay, now once if I learn the energy stored in this capacitor and all, etc., those terms were done. Once the terms are done, and then we can go into the next upcoming circuits and some kind of examples we can directly learn. So let us learn about now energy stored in a capacitor. What was the topic now we are learning about? It is energy stored in a capacitor. energy stored in a capacitor. Okay, so now what happens over here? I will just give you a flow chart. Understand? Try to understand a flow chart. When a capacitor, see here, when a capacitor is connected to a battery, remember, when a capacitor is connected to battery, what do this battery will do? What does this battery do? This battery transfers positive charge, transfers positive charge from which plate to other plate? Negative plate to positive plate. Negative plate to positive plate. And what do you mean by this one? To move this one, I am just making sure that there is some work done. So therefore I was performing some work, or say work is said to be done in transferring that charge. Work is said to be done in transferring the charge straight away. And this work, whatever it is done in transferring the charge, is stored in the form of electrostatic energy. That's it. So this energy is called as energy stored in capacitor. So electrostatic energy. So thus energy stored in a capacitor is given by U is equal to half into QV. Just remember the formula, U is equals to half into QV. So we have different forms, right? Where first form is Q is equal to C into V, from which I get potential energy stored or energy stored is equal to half C V square. And already I have V is equal to Q upon C, from which I get U is equals to Q square by 2C. So these are also a different forms of energy stored. We can use any of the form for finding the energy stored in the capacitor. So half QV or half CV square or Q square by 2C. Q square by 2C. Now let us learn some points in this. So first one is work done. Same thing. Work done in charging a capacitor. Work done in charging capacitor from potential V1 to V2. So for this one, what I can write the formula as? For this I can write the formula as work done W is equal to change in the energy stored. And so therefore from this, work done can be written as only potential is being changed, right? So I can use the formula half CV square. So half C into V2 square minus V1 square. See, it is similar to that of work energy theorem, right? Work done is equal to change in the kinetic energy. See, everywhere it appears, right? The physics is a bit easy, I guess. From all these cases we can see, right? So therefore there are some forms and all etc, and let us learn all those things also. So done. Okay, and there are some group of capacitors also there, and for that group of capacitors also energy stored I would like to give you. So therefore potential energy or energy stored of group of capacitors, so which all I need to take it on. Okay, so what are the group of capacitors? I have series and parallel. Any combination it could be. For any combination it could be total potential energy. Total potential energy, that is U, is equal to individual potential energies. U1 plus U2 plus so on. Let it be any. Okay, and if that capacitors are connected in series, if those capacitors are said to be connected in series, then U1 is to U2 is to U3 is equal to simply Q square by 2C1 is to Q square by 2C2 is to q square by 2c3. Since charge is constant, I can write this one as 1 by c1 is to 1 by c2 is to 1 by c3. And now if by any chance they are connected in parallel, the capacitors are connected in parallel by any chance, then I can simply write, you can expect, yes, very good, u1 is to, u2 is to, u3 is equal to c1 is to, c2 is to c3. So these are a kind of things which you need to remember for sure while doing the capacitance numericals, right? So now there is one more important kind of thing we would like to learn here, that is sorry guys, electrostatic energy density. What was that called as? Electrostatic energy density. Electrostatic energy density. So already we are most familiar with these words, right? So one among this one now here is electrostatic energy density is defined as or given by UD, that is nothing but energy stored in the capacitor per unit volume. That's it. So that is equal to what I can write, half C V square by volume can be written as area into density. Sorry, area into width. I can write this one as area into width. So now these all can be rearranged as, look at here, half into capacitance can be written as epsilon naught A by D into V square can be written as electric field into width whole D square, and by what was there here for me, A into D. Now you can say area cancel, d square get cancelled. So this can be written as electrostatic energy density is equal to half into epsilon naught into E square. The same thing we will learn in magnetism also, half into mu naught into B square. Energy stored per unit volume in magnetism. So see, these all the things we will be learning one after the one very easier. And the next concept for this understanding is force between plates of a capacitor. Force between plates of a capacitor. So I would like to just skip the derivation. Okay, I would like to give you a clarity what all the terms are present in this, and I would like to explain or give the formula for this straight away. If anyone requires the derivation, you can just text me in the comments. I will just share the what you call so-called the derivation in a new video. So now this is say plus Q and this is minus Q. Let me suppose the electric field is going to be in this direction, due to which the force will be acting on this in this way. F is equal to Q into E because of one of the charged plate. So therefore straight away F is given by F is equals to Q square by 2A epsilon naught. F is equal to Q square by 2 epsilon naught. So this is the force by plus Q on minus Q plate. Plus Q on a minus Q plate. And already what is the formula I have? Q is equal to C into V. Just substitute Q is equal to C into V to get F is equal to half epsilon naught A E square. Half epsilon naught A E square, where E stands for electric field. The same previous derivation whatever we did. We can use this formula to find the force between plates of a capacitor. Okay guys. And next, sharing of charge or redistribution of charge. Okay. There are some questions which will be asked on this concept whatever I am saying now. Remember, sharing of charge or redistribution. Sharing of charge or redistribution of charge. Now try to understand this combo, whatever I explained here. I mean, like I would like to draw the diagram. See here, just try to understand what was they are trying to explain. So now this is one capacitor and this is the another capacitor. I just give you, and now these two are connected in such a way, parallel. But here there is a switch. There is a switch, and say it's holding a potential V1, it is holding a potential V2, and having a charge Q1 and having a charge Q2. Say this is positive plate and this is negative, and this is positive plate and this is negative. Clear? And what will be its equivalent? This is will be equivalent Q and equivalent C equivalent, and equivalent potential is V. There's a diagram actually for these two things will be there. When once the switch is closed, remember, when once the switch is closed, what is happening? The total charge will be equal to sum of the charges Q1 plus Q2. So what is going to be this one? C1 plus C2 into V, correct? Because that is in parallel combination. And what was this Q1 means? C1 V1 plus C2 V2. Now this is a question they will ask, what is the effective potential? What is the effective potential or potential of the combination? That is C1 V1 plus C2 V2 by C1 plus C2. Most important, guys. And next, the next question they are going to ask you is, what is the change in the energy due to this thing? So U final minus U initial. So for this I can write change in energy is equal to half into C1 C2 by C1 plus C2 into V1 minus V2 whole square. You can use this formula for finding the change in energy, which will be appeared over there for this combination, sharing or redistribution of charge. Clear? And if connection was made in a different way, the connection was made in this way. If positive plate of first capacitor is connected to negative plate of second capacitor, then the formulas are gonna change for you, as the effective potential V is going to be C1 V1 difference C2 V2, which is heavy, which is greater, that one you can use, by C1 plus C2. This remains constant as usual, and then change in energy delta U is equal to same half into C1 C2 by C1 plus C2 into V1 plus V2 whole square. So this is the difference. I mean, like they are connected in series in that case. Okay. And most once they have asked, I guess, this question, redistribution of charges. Two charged particles are connected using a wire or connected by a conducting wire. What is the effective capacitance or what is the energy stored, all etc. So let us see that model also. So redistribution of charges, redistribution of charges, and that too conductors connected with wire, conductor connected by a conducting wire. So in this special case, what's exactly going to be conducting wire? So I would like to take two conductors having some capacitances, like charged spheres only I would like to take. Say this is one sphere and this is the another sphere. Say its capacitance be C2 and it is a positively charged, and say its charge be Q2 and it is also positively charged, charge be Q1 and its capacitance be C1 and its potential is V1 and its potential is V2. Now say that these two are connected with a connecting wire or conducting wire in this way. So the net potential for these two will be V is equal to C1 V1 plus C2 V2 by C1 plus C2. So now here the point is, this can also be changed as R1 V1 plus R2 V2 by R1 plus R2 radii, and C effective or C equivalent or capacitance. Effective capacitance is given by straight away Q1 dash plus Q2 dash by effective V, and that is equal to simply C1 plus C2. And the change in the potential energy stored because of this connecting or conducting wire, that is given by half into 4 pi epsilon naught in terms of their radius, written the capacitances by R1 plus R2 into V1 minus V2 whole square. So this is the formula we can use for such models whenever they are asking you kind of questions to solve it out. Okay, and as I promised you that there are some topic or some bullet points where we can remember when the dielectrics are being given, an effect of dielectric, how it is going to be. So before going to learn that, I would like to explain effect of union of identical charges or charged liquid drops to big drop. Okay, na? So therefore, effect. What would kind of effect? So union of identical charged liquid drops. Smaller charged liquid drops are there, and these all are unioned into a big drop. These all are unioned into a big drop. So therefore, for big drop, I would like to write all the cases. So for a given big drop, where all the small drops are being union to form this big drop, what are all the cases going to be changed? So the first one, radius of the big drop is equal to n to the power 1 by 3 times r, and charge on big drop is equal to n into q, where n stands for n number of identical charges. And third, capacitance of the bigger drop is equal to n power 1 by 3 times capacitance of each smaller drop. And fourth, surface charge density of bigger drop is equal to n power 1 by 3 times surface charge density of each smaller drop. And next, potential of the bigger drop is equal to n power 2 by 3 times potential of each smaller drop. And energy stored or potential energy of bigger drop is equal to n power 5 by 3 times potential energy of each smaller drop. So these are the few uh, conclusions we can have when some unidentical charged drops or liquid drops are union to form a big drop. So other than this, now I'd like to give you that important points where effect of dielectric is making here for you, and what are all the conclusions we can have for that effect of dielectric for numerical simple understanding. So note point I can give you as a note point. So note, that is effect of dielectric. Effect of dielectric, and with a constant k, who is having a constant k when inserted. What are all changes it can make? Okay, now what all changes it can make is the first one. Okay, potential difference. First one, potential difference remains the same. Most important, guys, try to learn or try to understand this. Potential difference remains the same. And second one, capacitance becomes, already I said, k times C naught. Third, charge becomes k times initial charge q naught. And fourth, electric field remains same. Right? And at the same time, fifth one, charge density sigma will become k times q naught by a. So k times, it will become the previous charge density, so K times sigma naught. And sixth one, potential energy, U, becomes K times initial potential energy. Okay, and the next one, seventh, change in the charge transferred or additional charge passing through the battery will be initial charge into K minus 1. And next, additional work done is equal to Q naught into V into K minus 1. So these are the few conclusions we can have. And next, see, this is important, guys. There are some PYQs on this concept, what I am writing now here. When a capacitor, listen carefully, when a capacitor charged, listen, when a capacitor is charged and then disconnected from the source, and a dielectric of constant K is now inserted between plates. What are the changes will happen? Okay, what are the changes are going to be happened in this case? So these conclusions will help you a lot, guys. First one, charge Q remains same. In this case, charge Q remain same. And second one, capacitance changes, becomes K times C naught. Third one, potential difference becomes 1 by K times. Potential difference becomes 1 by K times initial potential difference. And fourth, electric field also will become 1 by K times initial electric field. And fifth, surface charge density remains same. And sixth, potential energy also becomes 1 by K times. Initial potential energy. Clear? And next, one more case was there for us. What was that? When plate separation between the capacitor plates is made n times. What was this? When the plate separation between the capacitor plates is made n times. So now this is the next topic. See, these are shortcuts while solving the PYQs which will help us for us. Okay, so what are all the things are going to be happening? So first, connected to the source. Initial, I can say connected to the source. Over here I will write connected to source. And here charged and disconnected. So the tabulating the things I can just show you here. The first one, in this V remains same. Here who remains same? Q remains same. Next, here C becomes 1 by n times. And here also C becomes 1 by n times. And here third one, Q becomes 1 by n times, but here V becomes n times. And here sigma turns to be 1 by n times. Here sigma remains same. Sigma remains same. And in this case E turns out to be 1 by n times. And here as usual E remains same. And last but not the least, energy becomes 1 by n times. And here energy becomes n times. So these are a few conclusions where we can use the logic while solving the PYQs on the capacitors things, right? And there are some circuits also there, like Wheatstone bridge concept and other form of Wheatstone and Kirchhoff's laws are there, loop law, etc. So all those stuff we will learn in our next video, that is solving PYQs with the capacitor concept as well as circuits in like Kirchhoff law and Wheatstone bridge concept, and some other questions we will be trying to understand in our upcoming video. Okay guys, so thank you all, have a great day and hope you understood. Any doubts are there, you can just ping me on my comment section, just we'll sort it out the doubts clearly. Thank you all, have a great day.